Okay, so this is the first set of notes in Unit 3. It is on inductive reasoning. And we're also going to take on conditional statements and biconditional statements. Okay, so inductive reasoning is reasoning that's based on past observations. So somehow I've observed something, I tend to see a pattern, and I draw a conclusion based on that pattern. So, like, if I give you a little kid's pattern like red, red, blue, red, red, blue, red, red, and asked, what do you think is the next space? Then you can make an observation. It looks like it's 2 reds followed by a blue, 2 reds followed by a blue, 2 reds, and a pretty logical conclusion to draw here would be that this is going to be a blue. Now, let's talk about what's going on here. You've made a conclusion based on past observations. Now, the problem here is that there's a high probability that you're right. But it's only a high probability. It is not certain. Or another way that we can say this is it's not necessary. Right? We have evidence to support that the answer might be blue, but in fact it's not necessary. So for example, this pattern could be red, red, blue, red, red, blue, red, red, yellow, red, red, blue, red, red, blue, red, red, yellow, and so forth and so on. And it might keep carrying that red, red, blue, red, red, blue, red, red, yellow, red, red, blue, red, red, blue, red, red, yellow pattern. And then in that case, our conclusion would have been wrong. So given the evidence that we have, there is a high probability to support my conclusion, but that is not necessary because, not a necessary conclusion, because it might be that at some later point, another observation might defy our pattern or material here. Now, there is a way in very, very, very small circumstances, and we'll see it later this year, where you can actually get necessary through an inductive process, but it's a very, very, very limited scope of things. So generally speaking, if you're doing inductive reasoning, you will only have a high probability of a correct conclusion and not have a necessary conclusion given the data that you have. Okay, the other form of reasoning that we tend to use is what's called deductive. And deductive reasoning makes a logical argument based on accepted statements. And so this isn't on observations, but it's on accepted statements. So things in this could include things like definitions, postulates, proven theorems, what are called corollaries, which are tiny theorems, or just given information. Okay, so the conclusions here, oh, that's not good. Let's try that again. Conclusions here are necessarily true if hypotheses are true. So if you have a true hypothesis, then the conclusion must also be true. So these are specialized terms, conclusion and hypothesis. And these are part of what we are going to call conditional statements. Okay, so a conditional statement. A conditional statement is an if P then Q type statement. So like if today is Tuesday, then tomorrow is Wednesday would be an example of a conditional statement. So we call the P part of the conditional statement a hypothesis. We call the Q part of the conditional statement a conclusion. Okay, so what's going on here? This is like the tool that we use to make deductive logic work. If this is a true sentence, like if today is Tuesday, then tomorrow is Wednesday, that's a true statement. So, if the hypothesis is true, the conclusion must follow. So if in fact today is Tuesday, then tomorrow must in fact be Wednesday. Okay, so a true conditional statement allows us to move from one accepted statement to another, so long as the statement itself is true. Okay, so that's a little bit confusing, but we'll look at that as we're going through this year a bit. But this is the big key tool that's used in deductive logic, is the conditional statement. Alright, so we have a little bit of work to do here, so let's hold off on this. Okay, so we've just said that a conditional statement is something in the form of if P, then Q. Now, we also have a related statement to this, which would be its converse. So a converse takes the original conditional statement and switches the P and the Q. So the converse would now say if Q, then P. So let's give another example of a conditional statement and see what's going on here. Like if I had the original example, I have something like if today is Tuesday, then tomorrow is Wednesday, and I take the converse, which says if tomorrow is Wednesday, then today is Tuesday. It appears that the conditional statement and the converse are both true. Okay, so in that case, the conditional statement is true, the converse is also true, so that looks like that these both have to be true together. But the fact is that's not the case. Okay, so let's look at another example of a conditional statement where that doesn't quite work out. Let's try if I am a Garrison Forest student, then I attend an independent private school. Well, okay, that's true. All Garrison Forest students attend an independent private school. But the converse of that statement would be if I attend an independent private school, then I'm a Garrison Forest student. That's definitely not true. I mean, students go to McDonough, they go to Gilman, they go to Roland Park Country School. So they're all independent school students, and none of them go to Garrison Forest. So in this case, I have a situation where the conditional is true and the converse is false. So this tells me something. I can have the conditional be true And I can end up with a converse that's either true or false depending on the circumstances. So the truth value of the converse has nothing to do with the truth value of the conditional. So just because you know this is true doesn't mean you know anything about this. So these are unhooked. Their truth values are not the same. Okay, so this leads us to something that's called a biconditional statement. A biconditional statement is something that reads P if and only if Q. So this is a combination of two things. This combines, one, if P, then Q, and two, its converse. If Q, then P. So what has to happen here is, in order for this statement to be true, both the conditional must be true and the converse must be true. So in order to prove this type of statement true, a biconditional statement, you have to prove first the conditional, if P then Q, and you have to prove the converse. You have to prove them both to be true. So the biconditional statement, today is Tuesday, if and only if tomorrow is Wednesday, would be true, because the conditional statement, if today is Tuesday, then tomorrow is Wednesday, is true. And if tomorrow is Wednesday, then today is Tuesday, is true. So then we can legitimately say that today is Tuesday if and only if tomorrow is Wednesday. Okay, so that being said, that gives me an example of a biconditional statement that is true. Now, take our second example. A person is a garrison for a student if and only if that person attends an independent private school. That statement is false. Why would that be false? Well, the conditional is true. If a person attends Garrison Forest, then they attend an independent private school. Woohoo, we meet that one, it's true. But we're no good here. If a person attends an independent private school, then they attend Garrison Forest. No, not true. So since that's not true, also the biconditional is not true. So in order for a biconditional statement, an if and only if type statement to be true, both the conditional and the converse must be true. Okay, so let's summarize what we said today. You have inductive reasoning. Inductive reasoning is reasoning that comes from observations, right? And it is highly probable, but not necessary, the conclusions, right? So the conclusions are highly probable, but not necessary. Deductive reasoning comes from accepted statements. And in deductive reasoning, if you have a true hypothesis, then you are required to have a true conclusion. So if the hypothesis is true, then the conclusion will be true. A conditional statement is something that has a hypothesis and a conclusion. It's a statement that reads, if P, then Q. Okay, so if I have something that the hypothesis leads directly to the conclusion, then I have a true conditional statement. If I have a converse, that's taking the original conditional statement and changing it from if P then Q to if Q then P. So that's the converse. These two things do not necessarily have the same truth value. The conditional can be true, and the converse can be either true or false. Okay, so finally we have this idea of a biconditional. And a biconditional statement, which is something of the form if P, sorry, that's not true, should be P if and only if Q. And in that case, both the conditional that it comes from, if P then Q, and the converse, if Q then P, must both be true. So it's a bit of a summary of what we've done in this video.